So yesterday I've discussed what the linear types extension does, and I think you might have gotten the impression that this is only an extension to the type system. And in a sense, this is true. Linear types do not provide out-of-the-box extra performance or better optimizations, anything like that. It is just a different version of the arrow. So in a sense, linear types do not give you any performance at all if you think only about the changes inside the compiler. However, languages do not exist in a vacuum. A language is useless without its libraries. And one of the motivations behind linear types is that using this linear function arrow, it is possible to build interfaces that are more performant than interfaces you couldn't build without linear types. One example is arrays. So in Haskell, I think we overuse the list type. Everything is a list, and lists are simply bad. Because to traverse a list, you go through pointers, and the different pieces of the list can be in many different regions of memory. Any cache locality is broken. You don't have random access to the fifth element of the list. You have to traverse it. Calculating the length of the list requires traversing it, and so on. Lists are simply terrible, but they are used everywhere. What do languages other than Haskell use? Arrays. Now, why can't we use arrays? Well, we can have a block of n items stored in memory. The problem is with duplication and referential transparency. If I have an array A, let's say it's an array of integers, the issue is what I can do is I can say let's write to A in one function, and then let's do some computation. So let's say I will write to A on index 1 the number 10, and somewhere else I will compute the sum of writing to A third position number 30. The problem is that when I write to an array A, since I'm overwriting some region in memory, this can affect other pieces of code that also are reading from the same region, from the same pointer. Therefore, we don't have referential transparency. The order of computation, the result depends on the order of computation. So how do you resolve this problem? The normal way in Haskell is to use the st-monad. And that works. So in st, you just say, let's create a new reference. All your operations are, there is an explicit sequencing on your operations because you combine everything using binds. The problem is that this forces an ordering of computation, even if that ordering is irrelevant. For example, your code might create two arrays, read and write both to both of them, and the way your code is written must specify whether you read the first array or the second array. If you have linear types, there is a different solution. The solution is that we make the array linear, and this means there will be no aliasing. There will be only one place where we access the array. This means we won't have this problem with referential transparency. In other words, we can mutate the array in place. While previously, we either had to use the st-monad or we had to copy the whole array so that other users of the array wouldn't notice our change. So how do we do that? Here is a simple API, and this API is not implemented. I'm only presenting function signatures. Let's start with simple things from yesterday. This is a folding operation, and I made it linear in B. So currently there are some issues if you try to make it multiplicity polymorphic, but they are doable. So we would have this generalization of fold L, which threads this accumulating value B in a linear way. And the code of fold left is exactly the same as the normal fold left. There is exactly no change. You can do the same thing with fold right. So what's the API? I have only 4 functions here. There could be more. The first function creates a new array. And here we are using the unrestricted type from yesterday in a very specific way. We are making a linear function that is returning an unrestricted value. This might remind you of the movable thing from yesterday. Something that is movable is just information, is not resource. So what new array does is it takes its integer, it takes this callback, it calls this linear function giving a mutable array, and it expects an unrestricted result. In other words, I can't just say that B is M array A because M arrays are not movable. Normal, non-mutable arrays are movable. I can just share the pointer, and since they are not mutable, this is not a problem. So what can I do given a mutable array? Well, this mutable array is now kind of a hot potato. I can write to it, but I get it back. I can read from it, but I get it back. And at some point, I need to decide what to do with it. Well, I could add a drop function. And if I have this drop function, I can create an array temporarily. I can read and write to it. But at the end of the computation, I have to discard the array. And this is enforced. The other thing I can do is freeze an array. Freezing an array, normally in Haskell, if you would freeze an array, a mutable array, you would have to copy it, right? Because someone else could modify it after you freeze it and you will have a problem. However, thanks to linearity, you don't have to do that. What you can do is just mark the same region of memory as no longer mutable. So this freeze operation does not do anything. It's not even linear in the number of array, it's constant time. And thanks to this trick, we can have algorithms which operate on arrays, do not use stmonad, use mutation under the hood, and they are pure. And there is no st So how would we implement an algorithm using this? Well, this is a bit roundabout because we need to thread this array, right? So you might complain this is really bad that we need to thread it, but in fact we are writing pure code. So when you write a pure code using arrays, you would do the same thing. It's just you are now writing pure code, except you get better performance. So this is the first version that hopefully will work in the final version of linear types. And now, due to issues with inference, it doesn't. However, this code should work. And I'll present a fixed version which does. So this is a function that takes an integer and returns an array of integers. And since I couldn't think of a better example, I just picked Fibonacci numbers. So what do? We get this array R, and we start by writing to this array. At the position 0, we write 0. At the position 1, we write 1. Then this init array is our array initialized with the two initial values. Then we'd like to go through the entire array and compute every number. So what we do is we use a fold, this fold, over 2 until n-1. Given any integer I, what we do is we take this. The array from the read call, and notice we are getting it back. So this way we are reading the position number I-1. We are reading position I-2, and we are writing the sum. We need here to pass this array around. If we had borrowing, we wouldn't have to do that. So this might remind you of the examples with sorting and partition from yesterday. Finally, we freeze the resulting array. So this algorithm is implemented using mutation under the hood. If we used the normal pure arrays, it would be quadratic, because at every time we write to an array, we would have to recreate it from scratch. And there is nothing monadic in here. Notice that we could have multiple arrays, and then we could interleave. Here we are training one array, and we are forced to do that because there are data dependencies. But we might as well have two arrays, and then the computations on them might be performed independently.
In this example, do we need, I mean, I know the API is like that, but do we need the fib1, fib2 to be unrestricted? And if not, could we have an API for the arrays that would return restricted values?
That's a good question. The answer is no, because you can call read multiple times. So this API does not prevent you from reading the same entry in an array multiple times. Right? So let's say,
I mean, if we removed unrestricted, I would still be.
If you remove this unrestricted,
yeah.
Yeah, that still works, but the API is less powerful, right?
Because I can only read once from a given index.
No, because you are getting this array A, and now you need to you have to consume it linearly.
The value that I've gotten out of it.
Yes.
Isn't that what we want in this particular example?
No, what we want is the linear array itself to be consumed linearly, because we are threading it. But the elements of the array could be integers, and we don't have to thread them linearly.
But if we had the opportunity and we wanted to, I mean...
So the problem is, if you'd like to change read, if you'd like to thread those values linearly, if you'd like to store, say, other arrays here, what you would need to make is this write operation would take a linear value of A. Right? Like the interface you're proposing is just less powerful. Yes. We need to make a trade-off somewhere, and the most obvious way would be to say that yes, you can get linear arrays from A. That's less powerful, but in return you have to write linear values to A. Right? Mm-hmm. So the way this would work, I guess, is that you could write to array, but reading from you could write to the array. But if you read an item from it, it will be popped and it will be removed. And you couldn't overwrite an existing element, because that would be destroying it. Okay, so the API would be a bit different. This would not be like a normal array. This would be, it would not be a queue, because a queue is not random access. Yes. It would be like a storage thing, where you can have something or you don't have it. Right? Like.
And also, I guess, coming back to the example, we need to read each element of the array at least twice, right? Because we take the previous and the previous one to compute the current. Mm-hmm. So we can't really make Fibonacci linear, right? Or can we?
Well, reading from an array is constant time. This is an array, not a linked list.
Concerned with linearity, whether we could have a totally linear API for arrays and use it to implement Fibonacci.
I don't understand the question.
Yeah, maybe let's move that.
So this is an interface for linear arrays, right?
Yeah.
Now it is true that Fibonacci numbers can be computed without an array. You just store the last two, and you can return them as a stream or as a list.
Yeah,
right. The issue with that, imagine some different Fibonacci numbers which say, so Fibonacci have recurrence relation fib of n equals fib of n minus 1 plus fib of n minus 2. And you could just keep them, you could just keep the last two values computed, right? And that would work as well without an array. However, imagine you have this relation. I divide by 2, right? This is much harder to accomplish without an array. This is like a dynamic programming algorithm. So yes, so what I wanted to emphasize here is that this unrestricted trick makes sure that this mutable array does not escape from new M array. right? So the scope of this M array is ensured to be only within this function. It cannot escape. This might remind you of the for all S in ST monad. If in ST everything is tainted with that S and we need to be polymorphic over it, so that's why you can't a reference cannot escape from ST. And here we use linearity, and we require an unrestricted value as a result to get the same to get a similar effect. One more idea is if you think about the ST monad. Well, you can think that it's kind of the linear state monad where the state is a heap. Right? So this is how you could, it's not literally how it's implemented, of course, but this is a way of thinking about it, that ST is a special case of linear state monad. It's just the state is an entire heap instead of just one array. And here we are explicit and more fine-grained what the dependencies are.
Isn't the same with I/O?
Yes, with I/O. So GHC implements I/O in a pretty special way. It's real world to a real world, right? Something like that. And this real world is just a token. When you compile a program, it disappears. And those become like a nullary functions which have side effects. The problem with this real world token is that you'd like to ensure that it's executed, it's passed linearly. So when you say do print A and do print B, internally this becomes the state monad, and you want this to be threaded correctly. Because if you rewrite it, and if you could make optimizations based on the fact that real world contains no information, then what could happen is that GHC would reorder those instructions. Right? If the compiler could make an optimization, real world does not contain any value at all, the compiler could just reorder print A and print B. Because right, it's like the unit type, contains nothing, so you kind of don't have to compute it.
So you're saying that the optimizations that are in GHC currently don't do that error, that bug, but having linear types for I/O, for the
yes. So currently this is not checked in the compiler, and there are places that need to be careful because of real world. Otherwise, you could have bugs. There are also things like the state hack that might cause sometimes surprising behavior. What we could do if we have linear types is we could say that this real world is linear, right? And in this case, this A probably would have to be unrestricted. What we want is this real world to be threaded in a linear fashion, kind of those arrays. Okay, so I've mentioned that, this is ideally this is how you would write it. Unfortunately, due to implementation constraints, currently those let bindings cause the argument to be consumed as a in an unrestricted way. So the implementation that compiles looks like this, and there is no let statement, and this let statement is simply replaced by pattern matching. So it's really the same code except written in a different way. Yes, it is a bit more verbose, and I hope in the final version it will look nicer. Okay. Files. When you open a file, you would really like to close it, and after you close a file, you really won't want to read from it. Now, how do you do that? In Haskell, there is a function called withFile. Right, withFile takes a file path, takes a file, you do IOA, and you get IOA, right? So what's the problem with withFile? Yes, it works, it closes the file, it even works well when there are exceptions, and the problem is it doesn't guarantee that the file handle won't leak. Because what I can say here is I can put the return function here. Right? if I behave nicely, if I create programs like with file lambda with file full txt, I get this file f, and now I say read file. Later I can say print out a, and write file. That is safe. But imagine I write this. Right? What will happen is that the file handle will be closed, and you will get a closed file as the return value. So while with file works, it is a very nice pattern, much better than opening and closing a file manually. It is not foolproof. It has a hole. And you can use linear types to plug this hole. So this needs a linear variant of the I/O monad. In I/O, you have, in any monad, you have the binding operation. Right? So binding is I/O-A to I/O-A, I/O-B to I/O-B. Now, for this to work properly, you would need those arrows to be linear. And in fact, it can be multiplicity polymorphic. I won't go into this, but you can just pretend that I/O is treating every resource linearly. So if you open a file, you get a file. If you read a line, this file is given to you linearly, and you get it back, and you get the result of reading it, and finally you can close the file. So assuming I/O is linear, and it is requiring this file to be used linearly, this API enforces proper file usage. That files that are closed, once you close a file, you no longer have access to its file handle. And unlike the array API, we have a monad here. We need sequencing because file operations are not commutative. It doesn't matter in which order. If you write to independent places in memory, you can rearrange them, but we don't want to do that with files because writing files is basically a side effect. Yes. Okay. A similar approach is sockets. A socket is, yeah, I have the API here. So sockets are a bit complex. Maybe this one is more readable. Sockets can have multiple states. You have TCP and UDP. You can create a socket, you can bind a socket, and an unbound socket becomes a bound socket. You can listen, and then a bound socket becomes a listening socket. Once it's listening, you can wait for a connection, you accept a connection, you get another socket, and so on. Now, those operations have to be performed in a very specific order. This is like a finite state machine. And how can you enforce that this socket is used properly? Well, you don't need linear types to index that socket. You can do this already in Haskell, right? You can create your socket type and index it by the different states it can be in. However, there is still the problem that just like with arrays, the socket thing can be aliased. Someone else could, you might accidentally duplicate a socket, and then you lose all those guarantees. And just like with files, we need the I/O monad here. Okay, I have one more example. Computing directly with serialized data. So this needs a bit of explanation. Suppose you have a tree, okay, and you would like to use a remote service to perform some operation on the tree. Let's suppose you would like to multiply all nodes in the tree by 2. How would you do that? Well, you have this tree in memory, so you need to serialize it. You then send the serialized data via network to a different machine. That different machine needs to deserialize the data. It gets the tree type. That tree type is then operated on. Then you need serialization again. that piece of data is sent back, and finally you deserialize. So let me write this again. 1. So we start locally with a tree. The first one is serialize with a tree T. First step is we serialize tree on our machine. The second and send it to the service. Then the service deserializes to T. The first step is the service can perform computation on T, yielding T prime. The fourth step is the service serializes T prime to get something that can be sent over the network. And finally, step number 5 is that we deserialize getting T prime as the final result. Okay, so we are performing a computation. Let's say we are just increasing numbers in a tree or doubling them. But out of those 5 steps, 4 of them are just serialization. So it is conceivable that if this computation is not that complex, the majority of the time is spent on serialization and not on doing actual computation. Right? We have we do conversion 4 times. Can we do better? The answer is that with linear types we can. What we can do is, instead, the trick is changing this step. And if we change this step, the other 4 steps will be free. Instead of performing computation on trees directly, what we will do is we will perform operations on trees as if they were already serialized. So we won't have this data tree equals leave int or no of or node tree. Instead, we will be computing it as a byte string. Okay, so how would this byte string look like? It would be something like node, then, well, let's suppose that my tree is node 4, 3, 4, 4, and then leave 5. I can represent in the memory in the following way. I will just write it down. Okay. Now this representation has a few characteristics. It is a heterogeneous byte string. It mixes constructors and fields, and those fields could have different types. You can convert both ways. I hope you see this, just by keeping what is present. This representation, if you are in this node and you would like to jump to the right node, you can't. You have to traverse the tree as it's written. But on the other hand, this enforces that your program will be friendly to cache. Right? You make very local changes. You traverse the data structure in a very local way. Lastly, how would you write such a byte string? Well, this looks extremely error prone. If you make a single mistake, you will have a mistake in a binary format, and it will be a nightmare to debug. So the solution here is we will use linear types for writing. It is easy. If we have this node thing, what we can do is we can read from it. Read string. We'll either get an integer, or we'll call read recursively, and then we will get we'll get 2 strings, or to the left hand and the right hand side. So reading it turns out to be relatively easy. The problem is with writing. when we write, we must make sure that we don't write. If we'd like to write this node, if we'd like to write down this node, we must make sure that we do not write to the same pointer twice, as there are some invariants here. And the way to do that is similar to the trick with sockets. What we will do is, if you'd like to if you'd like to write down a leaf, you just write a leaf and the integer. If you'd like to write a node, you write down node, but the index of this of the serialization function will now remember that you still have to type 2 trees. Okay? So we will remember in an index that after writing node, you need to give you need to send 2 nodes. So notice that you can start. We have this needs type. If we are due to write a tree, if we still need to write a tree, we can start a leaf, and this puts the leaf token in our byte string. Afterwards, we need to write an integer. If we'd like to write a branch, then we index this with 2 trees. And again, just like with arrays, we enforce that this needs is threaded linearly. So we cannot abuse the system to write something that shouldn't be there. Finally, once this is finished, we have the empty list. This means that we have finished writing the whole data structure down, and we can get an unrestricted value of something that's packed, meaning it occupies a fixed region in the memory. Like arrays, we do not need I/O because we are writing just to memory, but we need linear types to make sure that we are not writing something bad. So the way you might think about it is that if we don't have an array and an index, the application is arrays. If we have I/O, but there are no indices, so this is the packed data structures. If we have an index and we are not doing I/O, this is the packed data structure, sorry. If we have an I/O and we are doing an index, this is sockets. Yeah, and if we don't have an index, we are doing just file operations. So this gives you like four different applications of linear types that are kind of connected. And they differ in their design. I have another idea is, suppose that you have a random number generator and you'd like to use it in some cryptographic situation. So you are getting a stream and you really don't want to reuse bytes, right? This is a situation where you could say that this stream is linear. You can do this already. You can already use a stream in Haskell. It's just you would have more compile time guarantees. Or you are writing a parser and you want to make sure that once a string is consumed, you don't go back, because that would be backtracking, and backtracking is bad. So again, you can make the stream linear. Or suppose that you are streaming, your computer does not have a lot of memory. By having the stream as a linear object, you can enforce that things are delocated and are not used anywhere and are ready for garbage collection. Or suppose you have a protocol that involves a client and a server, 2 remote services, and you'd like to make sure that when one party is listening, the other will send something, and the other way around. So you'd like to make sure that the protocols match. And you can do this with linear types too, if you add the index. So the index will be saying what party will send information and what is its type, while linearity will make sure that you are threading that those tokens, and you are not duplicating anything. Okay. Another example is making non-manifold models unrepresentable, except I don't have the internet connection.
You can use mine.
Jednak. So here I'm not an expert on this topic and I can't say much. However, this is a use of linear types in 3D printing. The idea is that you have an object like a cup and you'd like to make sure that it's watertight. You'd like to make sure that there is no hole. Like this cube with its front face removed is not watertight. And this thing has this triangle which can cause a crack. What you'd like to enforce statically is that every edge connects to faces. You don't want edges that are just connect to one face. And the way you can do that is when you create edges, you get two values that are linear, and they have to be later connected to faces in a linear way. So again, this is using linearity to make sure that some obligations are fulfilled. A similar example of enforcing some structure. Yeah, this is a bit exotic. This is called a rational tangle. So those are two pieces of string, and the goal is to untangle them. Okay, and given a description of this structure, it is possible to give an algorithm which will untangle it. And the way you do that is you write down this knot using some combinators like over, under. You specify the possible types of connections. You label every intersection using A, B, C, D, right? And then it turns out that you can represent the algorithm for untangling this mess by using the vector space monad and having those letters represented in a do block. Again, this code does not enforce linearity restriction, but because if we start with C here, we can only go to G. We cannot split the string. This is linear, and we might as well enforce this here. Yeah. So rational tangles are quite interesting, and here is a short video.
Twist, and one last twist, and voila.
Yeah. So the point here is that you can describe those pieces of string using those combinators, and and if you'd like to make sure that the combinators describe a valid state of the system, you can use linear types. Okay, this will be mostly it. I'll now have references for further exploration. This is the original linear Haskell paper. This contains most of the ideas, and I think it took. I think it's really readable. So it contains motivation. It explains the unrestricted type. It explains the example with packed and sockets in a more detailed way than I could do it here. There is one change that in the paper we allow the linear. There is a kind of an implicit cast. You can pass a linear function to a function that is to a higher order function that is requiring an unrestricted function, and the eta expansion is done here automatically. And we are not doing this in the implementation because there are some complex reasons. Now, those reasons and far more motivation is present in the GAC proposal. So this proposal has been conditionally accepted, and we'd like to finalize it. There are different approaches you can take to linearity. What I was doing here is linearity in a function type. A different approach is to have different types. For example, to say that every integer is unrestricted and every file is restricted. So this would mean you are splitting the universe of types into those which represent information and those which represent resources. So you have linearity in kinds. Or there is the approach taken by Rust or by Clean. There is uniqueness types. And this blog post, I think, is pretty readable comparison of very different design choices you can take. I mentioned code data on the last talk, and this is a paper about code data, connections to object-oriented programming, the duality you got between data and code data. I would say it's really readable, and how you can convert between data and code data. It's really readable, and it motivates code data a lot. Free theorems. I mentioned that a linear function must permute things. And I gave you a hand-waving argument that if it was duplicating stuff, it wouldn't be linear, or and it can't also discuss, it must be a permutation. Here there is a proof in Agda, a formal proof that this is true. Idris. Idris has uniqueness types, and I'd like to show a different application. Sometimes linearity does not force you to be correct, but it can guide you to be correct. So, in this talk, we'd like to write the transpose function, and it's taking a vector of n element, so a vector containing n element, a vector with n elements that are vectors of m elements, and we'd like to transpose it, right? And you could write it recursively, and now ask your type checker, acting as an assistant, to write this function for you. The problem is, if you ask it, you get something weird, like those parameters are completely ignored. Idris is putting empty types where it can. This is not what you want. And what you can do now is you can add a linearity annotation. You say you put this 1, and now if you ask Idris to guess the program again, you will get the correct program. So this doesn't mean you will always get the correct program, but this is a situation where linear types or uniqueness types can guide program writing. And here is documentation on this. Philip Water has a few papers about linearity. If you are interested in linear logic, there is a paper called A Taste of Linear Logic. It's a tutorial. It's more like rooted in type systems, but I found it very readable to get some intuitions about linearity. Finally, a paper by Mike Schulman, Linear Logic for Constructive Mathematics. So this paper, if you like intuitionistic mathematics, if you think about it being constructive, this paper takes it to the next level. And while a lot of that is, I would say, heavy mathematics, the introduction is very readable, and it points at some duality in linear logic. It shows that linear logic, while you can't get law of excluded middle, you can get double negation elimination. In intuitionistic logic, they are equivalent, but if you enforce linearity, you can have a constructive version of double negation elimination. So if you'd like to read it and you are scared about mathematics, I recommend reading the beginning and the end of the paper. Okay. Any questions? So I think we'll finish here. Oh, sorry, there is a question.
Sorry, I just wondered how to phrase it. So for your tree case where you have this serialization and deserialization, I have a particular case that is very interesting to me. So suppose you have like deserialization, then some operation on the tree, and then serialization, right?
Yeah.
So what you would probably like to do in some contexts is that you know that you change only fragment of the data structure, right? Which means that you have an algorithm that you could express on this data structure and just copy the remaining part of serialized representation, right? Can you somehow use linear types to do it? Or should I somehow rephrase the question so it's more
Yeah. So I'm not sure if I can give an answer right away. What you can do, there is a different approach than linear types, and there is something called compact regions. In compact regions, instead of having your tree structure all over the memory, you can say that I have this tree that is currently all over my memory, and it's horrible, and for memory it's horrible to access it. You can now pack it into one region of memory, and that region won't have any external dependency, so it won't garbage collection won't have to traverse it, and perhaps there you could make local changes.
This is actually a different question. So basically, there are a lot of programs that kind of maintain the database, right? The database that is basically serialized representation of some data structure. So every iteration of the program just reads the structure, so deserializes it, does some changes, and then serializes it back, right?
Yeah.
So you can imagine that this data structure can be huge tree, and the serialization of entire data structure can be complex.
Yeah.
Right. So one way to save some time is that to make the deserialization lazy. So basically, you only deserialize those parts that.
Yeah. So if you would just be reading a stream of data, I guess what you could do is you could just use the serialized version to browse through the stream, and only after you are ready you could use the unpacking function.
Yeah, so basically what I'm interested is in using linear types to somehow prove that we deserialize only parts of it so that we can keep it, right?
Yeah, I can't answer this off the top of my head, sorry.
Okay.
I would have to think more. Yeah. No more questions, looks like. Thank you.